Stand next to a spinning commercial jet turbine, and you will feel sound as a physical force. It is chaotic, kinetic energy tearing through the air. Put on a pair of noise-canceling headphones, flip a switch, and that roaring environment seems to drop away entirely. But the headphone hasn't actually created silence. The acoustic chaos of the room is still hammering against the plastic shell on your head. Rather than blocking the sound, the device is actively generating its own acoustic energy to fight it. A modern Active Noise Cancellation, or ANC headphone, operates as a wearable, ultra-low latency audio computer. Achieving a quiet environment requires running precise mathematical algorithms in real time, literally canceling incoming sound with perfectly calibrated sound. To see how this pipeline operates, we have to look past the exterior, separating the device into 5 distinct mechanical layers. The first subsystem is the acoustic seal. This relies on high-density memory foam and closed-back ear cups. This passive isolation acts as the physical front line. It easily absorbs the tiny wavelengths of high-frequency noises, like breaking glass or nearby conversations. Second are the MEMS, micro-electromechanical systems. These are highly sensitive microphone arrays, strategically embedded on both the exterior housing and the interior acoustic cavity of the device. Third is the digital signal processor, or DSP. Sitting on the main printed circuit board, this dedicated microprocessor executes one strict task: crunching audio algorithms in real time. Fourth is the digital-to-analog converter and its paired amplifier. Fifth is the electroacoustic transducer, the physical speaker driver resting against your ear. This driver faces a massive physical load. It must simultaneously output the high-fidelity frequencies of your music, alongside the DSP's precisely calculated anti-noise, without distorting either signal. These 5 components form a rigid, sequential pipeline. They capture, process, and output pressure waves at speeds that entirely bypass human perception. The hardware pipeline exists for a singular mathematical purpose, governed by how sound travels through space. Sound is a longitudinal mechanical wave. It propagates through the air as an alternating series of high-pressure compressions and low-pressure rarefactions. Activity called destructive interference. This oscilloscope plots an incoming ambient sound wave across a grid, defined as a function of time, x of t. The DSP generates a secondary wave, mathematically identical to the incoming noise. By shifting the phase of this secondary wave exactly 180 degrees, it creates a precise inverse function, minus x of t. When these two acoustic signals occupy the same physical space, the waves sum to exactly 0. The mathematics of phase inversion dictate perfect silence. But executing this inside a chaotic environment requires hardware architectures that predict noise before you hear it. To deploy a perfect inverse wave, the processor needs highly accurate intelligence on exactly what pressure changes are about to hit your ear canal. This cross-section of a headphone against a human ear illustrates the first data-gathering strategy, Feedforward ANC. By placing the microphone on the exterior shell, Feedforward operates as an open-loop system. It captures the ambient noise before it permeates the physical barrier. This early warning gives the DSP vital milliseconds to calculate the inversion. But since it can't measure inside the ear, it must guess the final acoustics, risking calculation errors from exterior wind. To solve this blind spot, we use the second design, Feedback ANC. Positioning the microphone inside the acoustic cavity forms a closed-loop system. The DSP hears exactly what your eardrum hears, giving it the ability to continuously measure the error and correct the anti-noise. The flaw here is time. If the internal microphone is detecting the noise, that noise is already striking your eardrum. To build a flawless response, engineers rely on a third design, Hybrid ANC. Hybrid systems deploy both arrays. The external feed-forward microphone does the heavy lifting, mapping the broad strokes of a low-frequency rumble. The internal feedback microphone operates as a precise calibrator, sweeping up residual frequencies in real time. These complex topologies exist to feed the DSP the cleanest possible data before the physical laws of acoustics render the inversion useless. The hardest physical constraint in this entire process is the inflexible speed of sound. Sound travels at roughly 343 meters per second. From the outer microphone to your eardrum, the signal only covers about 2 to 3 centimeters. This timeline illustrates this tight window. From detecting a pressure change, the hardware has roughly 60 to 80 microseconds to capture the signal, convert it to digital, calculate the inversion, and push the analog wave out the speaker. This brutal latency limit explains why ANC is highly effective at eliminating constant noise, like an airplane engine, but struggles with sudden sounds. Low-frequency sounds have incredibly long wavelengths. A 50 Hz wave changes slowly over time, giving the DSP an easy, predictable curve to invert. High-frequency noises possess tiny wavelengths that fluctuate wildly. If the processing pipeline is even a fraction of a millisecond late reacting to these rapid structural changes, the anti-noise will arrive completely out of phase. Instead of destructive interference, you trigger constructive interference. The generated wave stacks on top of the ambient wave, doubling the amplitude and increasing the volume. To prevent this failure, engineers program the DSP to roll off active cancellation at higher frequencies, handing the workload over to the high-density memory foam. Active noise cancellation is a relentless, zero-sum race against latency, where missing a microsecond deadline shatters the auditory illusion. Wear a pair of ANC headphones in a busy intersection, and you are subjecting this hardware to continuous, brutal stress. The processor is trapped in an endless loop, sampling thousands of acoustic variables, executing microsecond inversions, and deploying perfectly timed pressure waves. The plastic shell over your ear is completely transparent to the mechanical reality of the environment. It doesn't block the physical force of the city. Instead, it answers that force with exact mathematical precision. The resulting silence is an engineered environment. It is the product of fighting physics with physics, deployed directly into your ear canal.